Alright, hello, Algebra 2. We are working today on section 2.8. This is the last section of chapter 2, and we're going to be talking about a topic that we have done in previous math classes, which is graphing linear inequalities, and we're going to add to that absolute value inequalities. And it's not going to be that much harder because it's really the same principle for both. So our goals today are to graph linear and absolute value inequalities. So we just have two new vocabulary terms today, linear inequality, which actually isn't new, but look for the definition of that, and then boundary. Okay, so we're just going to do this by doing some examples. This is an example of a linear inequality. A linear inequality is an inequality that graphs as a straight line, and then you shade either one side or the other to represent the solution set. These are different from equations. In an equation, we just graph the line. When it's an inequality, we have a whole bigger set of points that make this true, because we need all the points that make x minus 2y is less than 4 true. So it won't just be the points on the line. There'll be a whole shaded half of the graph. When we have an inequality that's just less than or greater than without the equal to under it, we graph it as a dotted line. That dotted line represents that these points on the line are not part of the solution set. They do not make this inequality true. So what we're going to do is we're going to graph the line. The way to do that, there's a couple different ways. We're actually graphing the line, x minus 2y equals 4. And we can either solve it and we can put it in slope-intercept form. That would be negative x plus 4. And then we divide everything by negative 2. So we end up with y equals 1/2 x minus 2. And you can see that's graphed over here. Here's my y-intercept of negative 2. A slope of positive 1/2. Up 1 to the right 2, or down 1 and to the left 2. You can do that, or you would be able to graph x and y intercepts if you want to, and you would be able to graph it that way. But notice that they drew the line as a dotted line because the points on this line do not make the inequality true. For example, if we took the point 0, negative 2, that's a point on my line. If I were to plug in 0 for x and negative 2 for y, I would end up with 0 plus 4, and I would get 4 is less than 4. That is not true because 4 is not less than 4. 4 is equal to 4. So the points on the line are not included, but we do have to decide which side of the graph we're going to shade. To decide which side of the graph we're going to shade, we need to test a point. You always want to test an ordered pair, test a point that is not on your line. Okay? Test a point that's not on the line, because we need to figure out, do the points on this side of the line make the inequality true, or do the points on this side of the line make the inequality true? This line is called my boundary line. It's the boundary between the points that work and the points that don't work. So that's what a boundary line is. It's the line that I graph for my inequality. It's usually nice to test 0, 0 as long as it's not on the line. So in this case, we can test 0, 0. We're going to plug 0 and 0 in for x and y in my original inequality. And we end up with 0 is less than 4, which is true. Since 0, 0 is over here on this side of my line, that means that all the points on this side of my line are going to make the inequality true. So we're going to shade that region. We're going to shade that half of the graph, that side of the line. So we're going to shade all of that in, and that means any point that I pick in this blue shaded region will make my inequality true, not counting the points on the line. That's why it's a dotted line. Okay, why don't you guys try this one? Alright, you should have picked A. First of all, you'll notice that since this is greater than and it's not equal to, it needs to be a dotted line. So you could have thrown out C and D right away. Then you just had to figure out which side of the line to shade. If we plug in 0, 0 here, we get 0 plus 0 is greater than 10, which is false. Right? And since 0, 0 is on this side of the graph and it's false, we need to shade the other side, which is true. That leads us to answer A. Alright, let's look at a real-world example here. One tutoring company advertises that it specializes in helping students who have a combined score on the SAT that is 900 or less. So it can equal 900 or be less than 900. So that would be less than or equal to. Write an inequality to describe the combined scores of students who are prospective tutoring clients. X is going to represent the verbal score. Y is going to represent the math score. We're going to graph this inequality, but first we need to write the inequality, right? So X is the verbal part and Y is the math part. The scores added together have to be 900 or less, like we just talked about. So if we think about this in words, we're saying the verbal part and the math part together are at most, which is another way to say less than or equal to, 900. At most means less than or equal to because I'm saying the highest it can be is 900. It can be less than that or 900, but it can't go over. So that leads me to writing this inequality. X plus Y is less than or equal to 900. Now when I graph this, X plus Y is less than or equal to 900, I can solve it if I want to for Y. So I get Y is less than or equal to negative X plus 900. So my y-intercept is 900, and I have a slope of -1, and that takes me all the way over to 900 on the x-axis as well. That's my x-intercept. And then if we test a point, so let's say we tested 0, 0, because it's on one side of the line and it's not on the line. I get 0 is less than or equal to 0 plus 900, which is 0 is less than or equal to 900. That's true, so I shade the side of the line that contains 0, 0. Notice in this graph I'm only showing the first quadrant. The reason is because I'm not going to have any scores less than 0 in either direction. So I'm only going to have positive SAT scores. I only need the quadrant that shows positive X and positive Y, and that's the first quadrant. Alright, the second part of this question is, would this student who has a verbal score of 480 and a math score of 410 fit the guidelines? Would they be able to receive tutoring from this company? If we look back at our graph, if I look at the point 480, which is probably about right here, and I look at the point 410, it's going to be somewhere up here. Oops, I thought I was drawing that. Somewhere around here. That is in my shaded region, so that means it is part of the inequality. The other thing I could do would be to test that point in my original inequality. So if I do 480 plus 410, is that less than or equal to 900? That gives me 890 is less than or equal to 900, which is true. So that would be another way to show that that point does make this inequality true. So yes, the student would fit the tutoring company's guidelines. Okay, here's one for you guys to try. Alright, you should have answered B, less than or equal to 60. S plus C is less than or equal to 60. So in this case, they let S equal the number of students and C equal the number of chaperones. So the number of students plus the number of chaperones has to be less than or equal to 60 because there are only 60 seats on the bus. And try this one. You should have answered B. If you plugged this point into your original inequality, you would have seen that it did not make it true. And it's easy to see because 15 plus 47 is bigger than 60, larger than 60. And so it would obviously not work. Those amount of chaperones and students could not ride on the bus. Alright, let's try an absolute value inequality. We're going to graph y is greater than or equal to the absolute value of x minus 2. The good news is that this process is almost exactly like graphing linear inequalities. Okay, so the first thing we're going to do is we're going to graph the corresponding equation. So we're going to graph y equals the absolute value of x minus 2. And because this is greater than or equal to, it's going to be graphed as a solid line. Well, it's not really a line, a solid absolute value graph. Okay, so it's not going to be dotted, it's going to be solid. When we graph the absolute value of x minus 2, we get a graph like this. Remember that minus 2 outside of the absolute value moves the vertex of my absolute value from 0, 0 down 2 units to 0, negative 2. And then because there's no dilation, my sides remain the same. So this has a slope of 1, and this side has a slope of negative 1. And we graph it as a solid absolute value graph because it's greater than or equal to. If it just said greater than, we would have to make our V dotted. Then what we're going to do next is we're going to test a point. Again, I need to test a point that is not on my graph. In this case, 0, 0 is a great point to test because it's fast and it's not on my graph. So when I test 0, 0 in my original inequality, this is my original inequality, I plug in 0 for y, 0 for x, I get 0 is greater than or equal to -2, which we have here, and that is true. Since it is true, I need to shade the part of the graph that includes 0, 0. So in this case, it'll either be inside my v or outside my v. Since 0, 0 is inside my v, I shade everything inside the v. So any point I pick from this blue shaded region is going to make my original inequality true. And this time, because my line is solid, if I pick a point on the line, let's say we pick the point -3, 1, a point on the line is also going to make this true. If I plug in 1 for y and -3 for x, I end up with 1 is greater than or equal to 3 minus 2. 1 is greater than or equal to 1, which is true. So that is why we have a solid line, because the points on the line, or on the graph, on the v, make it true. Alright, you guys try this one. Okay, you should have picked b. The first thing you should have noticed if this was y is less than the absolute value of x plus 3. Since it's less than and not less than or equal to, it would have a dotted v, so we automatically knew that a and d would not be the correct answers. The absolute value of x plus 3 has its vertex at 0, 3, and so we just had to test a point and decide if I shaded outside or inside. And if you test the point 0, 0, you would find that it's true, and we would shade outside of our v. That is the end of this section, so I will see you guys in class to do some practice.